Okay, so here's our second example in for plate girder design. So we're going to have the same beam span as last time, same cross-sectional shape, so same top and bottom flanges, same web, same grade of steel. We're assuming that it's fully laterally restrained, so they're all the same assumptions as we had for example 1. Except in example 2, we put in a bigger load. So we now have a load of 420 kilonewtons per meter. That's ultimate limit state. Okay, so it's fully factored up, 1.35 dead plus 1.5 times imposed load. But in this example, we have the stiffeners, the intermediate stiffeners, at further distance apart. So we have them at 1400 distance apart, and in the center, the stiffeners are 1600 apart, and then 1400, 1400, 1400. Whereas in example 1, we had those stiffeners at 1250 apart. Okay, so again, like example 1, I've highlighted what the difference is, or what the main kind of subtle differences are in this example. That's what you have to be careful of when you do the designs. There's differences in each of the different designs, so you have to be careful to check all the scenarios. So in this case, what's going to happen is, at the moment, this is a moment in shear example where the flange has to contribute to the shear requirements. Okay, so if we remember from example 1, when we checked shear, we just had to use the web. The web alone had enough capacity to withstand the shear, and we didn't have to worry about the flanges. So the flanges could be just used for bending, and didn't have to worry about trying to carry any of the shear load or shear force in them. Whereas in this example, what's going to happen is that the flange is going to have to do some work in terms of resisting the shear force, and we're going into also having to do the moment of shear interaction check. So that's what that's the subtle difference in this one. And how is it different? Well, we have the same cross-section shape in it, with the same span in there, but we've increased the loading, and we've extended the spacing of the intermediate stiffeners, okay, or intermediate transverse stiffeners. So they're called transverse stiffeners because they're going up and down this way into the page. Okay, so we're going to determine if this section here is suitable to carry the shear forces and bending moments in there. Okay, so to be able to do that, obviously we need to know what those. So we're going to want to know what the shear force diagram and the bending moment diagram is, because we need to know what the demand is. So the shear force diagram. So again, this is a very simple load-in. So it's a uniform distributed load across it. Oops. So we're going to have a constant change in shear force as we go down through. So it's just going to be the load times the length. So that's the total load on the member. So load in kilonewtons per meter times the length in meters. That gives me kilonewtons. And then we know that half is going to go into the left-hand side, and half it goes into the right-hand side. Okay, so that's minus, and the load that factored up load was 420 kilonewtons per meter length times the length, which is 10 meters, all divided by 2. So it's 210 by 10, which is 2,100 minus, because we're down by kilonewtons. So that's 2,100 kilonewtons. Okay, so that's VED at the end. That's your design shear force. And the bending moment. So this is your demand on your member. The bending moment diagram, again, is 10 meters of a span. 10 meters of a span, and we know we can, it's either the area under the curve, under the shear force diagram, or we just know from, because we do this so many times, that the moment is equal to the load in kilonewtons per meter times the length squared divided by 8. Or if you get the area under that triangle, in L over 2, multiply by L over 2, because it's L over 2 here. So if I go in L, multiply by half the base by the perpendicular height, so in L over 2, multiply by L over 2, and a half of all that, that'll give you in L squared over 8. So again, if I just put in the numbers, 420 kilonewtons per meter times the length, 10 meters squared, all divided by 8. And that gives you 5250 kilonewton meters. Okay, so that's the demand. That's what we have to design for. This could be a bit better of a drawn shear force or minimum diagram. Okay, so that's what we have to design for. Moment, a maximum moment of 520, maximum shear of 210. But we have to remember that we check across the different panels. So we'll have to check panel 1, panel 2, 3, 4, 5, 6, and 7 in this section, because in panel 7 we have high shear, low moment. In the middle panel, panel 4, we have high or no shear but high moment, and then we have a medium moment and a medium shear somewhere along the way. So we need to check the different panels in there. So we're going to go through all our steps now for designing the plate girder, similar to what we did for the first example. Classify the section, we get the moment capacity, shear capacity, we check for moment and shear interaction, resistance to transverse forces, deflection check, and weld check. So there's the 7 steps we're going to go through. As I've gone through all these before, and it's available on the recorded lecture, only the new parts I'm going to start writing out from scratch. So classification of the section is going to be the same as for example 1, because it's the same cross-sectional shape. Even though we have the stiffeners further apart, it's the same cross-sectional shape, so therefore section classification is the same. So for section classification, we go to table 3.1 in Eurocode 3, part 1, part 1. First we need to, that's going to provide us what the yield strength of material is. We know that if the thickness of the plate is less than or equal to 40 millimeters, and we have grade S275 steel, then from table 3.1, thickness less than 40 millimeters, S275 steel, Fy is 275 newtons per millimeter squared. And our cross section, our flanges are 30 millimeters, our web is 20 millimeters. So therefore, both the flange has a yield strength of 275 newtons per millimeter squared, and the web is 275 newtons per millimeter squared. Okay, so that's the material strength of the webs and the flanges. Then we can go to table 5.2 in Eurocode 3, part 1, part 1. First, we want to do the web. So we look at the web for a welded section, which is shown here. So this is sheet 1 of 3 on table 5.2. And we want to get the unstiffened length of the web. The unstiffened length of the web is the height of the web minus twice the weld thickness. We have 6 millimeters for the weld thickness, 1200 for the height of the web. So that gives 1188 millimeters for the unstiffened height of the web. And then we need to divide that by the thickness of the web to get the slenderness of the web. So that's divided by 12, give us 99. And then we look at the limits for this guy. So it's in bending. So in 99, less than or equal to 72 epsilon, where epsilon is equal to 0.92, which is down here at the bottom of the table. No, it's not. Is it less than 83 epsilon? No, it's not. So it's not class 2. Is it less than 124 epsilon? Yes, it is, because 124 epsilon is 114, which is greater than 99. So therefore, it's a class 3 section. So we've classified it as a class 3 web. We then do the same thing for the flange. So again, this is a built-up section here. The unstiffened length of the flange, C here, which is from the outside of the weld to the very extreme of the flange. So that distance CF is going to be the width of the flange minus the thickness of the web minus twice the weld, all divided by 2. When you put that in, we get 238 millimeters. Thickness of the flange is 30 millimeters. So that ratio of the unstiffened length of the flange versus divided by the thickness of the flange is going to give us 7.93. And then we look at the part of the table subject to compression. If C over T of the flange is less than or equal to 9 epsilon, then it's class 1 section. Again, epsilon is 0.92 at the bottom of the table there. So we get 7.93 is less than or equal to 9 epsilon. Epsilon will be 0.92, so therefore it's a class 1 flange. So we have a class 3 web, a class 1 flange, so therefore the overall classification of the section is a class 3 section. So that's step 1 done, check the classification. Next step is to check the moment capacity. We'll go to Eurocode 3, part 1, part 1. and we know that we always have to check that what the demand divided by the capacity has to be less than or equal to 1. In other words, the demand has to be less than or equal to the capacity of the member. And that's equation 6.12 in Eurocode 3, part 1, part 1. We have a class 3 cross section, so therefore we go to equation 6.14, which tells us that the moment capacity is equal to the elastic moment capacity, where we use the elastic modulus, times the yield strength divided by the partial factor of safety, which is equal to 1. So that's the equation that we're going to use because it's a class 3 section. If this happened to be a class 4 section, because of the class 4 web, then that means that the web is susceptible to local buckling, and we would have to use equation 6.15 for that, where we have to work out what the effective modulus is for the section, which actually can happen regular enough for a plate girder because they're tall and very slender oftentimes. Okay, so we then have to work out what this elastic modulus is, and the elastic modulus is the second moment of area about the y-axis divided by the depth of the neutral axis. And for this section here, the depth of the neutral axis is 630 millimeters from the top down to the middle here, 630 millimeters. We know that the second moment of area for the section about the major axis is we've got the second moment of area associated with the two flanges. Plus the second moment of area associated with the web. So that's this part here. Working out the flanges, we use the parallel axis theorem, so it's the I for the flange itself, and then because it has a distance away, the neutral axis of the flange, away from the overall neutral axis of the section is 615 millimeters. So it's going to be the area of the flange times the distance away from the neutral axis squared. So that's AY squared. So the second moment of area of this rectangle up here is going to be just the width, B, times the thickness cubed divided by 12, which is there, plus its area, which is the width, B, times the thickness, TF, times the distance from the neutral axis in the member up to the center of that one, which is 615 millimeters squared. So that's what's put in there. And we get a value out here, 5.675 by 10 to the power 4, millimeters to the power 4. And then we look at the web. It's the thickness of the web times the height of the web cube divided by 12 into the formula there, and we get 1.728 by 10 to the power 9. So we can see that the flange, one flange alone up here is about, was it 3 times gives us 3 times the stiffness of the web. Of course, we have 2 flanges in there, so that 5.675 and multiplied by 2, one on the top and one on the bottom. So you're looking at the flanges are contributing about 7 times the stiffness as the web. That's so that's what we're trying to do, get this material out as far as possible to give it stiffness for minimizing deflection, but also to give it strength in terms of its moment resistance in there. Okay, so the overall second moment of area is just to add the second moment of area associated with the flange and that with the web, and we get that answer at the bottom there. Okay, so that's 13.078 by 10 to the power 9. And then the elastic modulus is equal to, so the elastic modulus is equal to the second moment of area divided by the distance to the neutral axis. So from the top of the member, so that comes out to be 20.76 by 10 to the power 6 millimeters to the power 3. And then we know that from equation 6.14 that the moment capacity is equal to the elastic modulus times the yield strength divided by the material factor of safety, and that comes out to be 5,708 kilonewton meters. So that's the exact same as we had for example 1, hasn't changed. What has changed for example 2 is we've got a bigger moment in there, so we look at the moment versus the capacity, having to keep that less than or equal to 1. That's according to equation 6.12. So what do we just work out the moment as? 5250 kilonewton meters. That's the demand divided with the capacity, 5708 kilonewton meters. So that's the demand divided by the capacity, and that's equal to 0.92. So 92% utilization, which is less than or equal to 1. So that implies it's okay. Okay, so that's the utilization ratio. We want to check, I suppose, to see, can the flanges alone withstand this bending moment, or do we have to use some of the web to withstand the bending moment in there? Because that will determine whether we have to do a moment of shear interaction check as well in there. So we just check those flanges. So we said from our classification that the flanges are class 1. So remember, in our step 1, we classify the flanges as class 1, whereas the webs are class 3. So when we go to 7.1.3, clause 7.1.3 in Eurocode 3 part 1 part 5, that gives us the equation. Tells us that the moment resistance from the flange, so this is the flange resistance, is equal to the area of the flange times the yield strength of the flange times the height divided by gamma m naught. Okay, so this is the plastic moment of resistance of the flange. Okay. So AF is obviously the area of the flange. Fy is the yield strength of the flange. And HF is the distance between the centroids of the two flanges. Okay, so we have one flange there, with the web, the flange there. This distance here is HF. And then you have BF, TF, so AF is equal to BF times TF. Okay, so we put all that in to the equation. So we have the width is 500, the thickness of the flange is 30, the yield strength of the material is 275 newtons per millimeter squared, and the distance from the centroid of the two flanges is 1230, because the web height is 1200, the flange thickness is 30, so 30 plus 30 divided by 2, which is back to 30, so 1230, and the material factor of safety, or the partial factor of safety, is equal to 1. So that's equal to 5,000, 74,046 Newton millimeters, which equals 5074 Kelvin meters. Okay, and then what was the demand? The demand on the section was 5250. Yeah. Okay. So the demand MED is 5250 kilonewton meters, which is greater than the capacity of the flanges to withstand that bending moment. So that implies that the need to check moment and shear interaction curve. Okay, for that middle one anyway, where the demand, so that middle section, the middle of the beam, where the demand is greater than the capacity of the flanges for withstanding the bending moment. Therefore, we have to design that or check for moment and shear interaction there. Okay, so that's moment capacity. Shear resistance. So again, similar to example 1. First, when we look at Eurocode 3 part 1 part 1, in clause 6.2.66 in here, it tells us that if basically this web slenderness, the height of the web divided by the thickness of the web, if it's greater than 72 epsilon over nu, then we need to go into section 5 Eurocode 3, part 1, part 5, and do our checks according to that. So in our case, we have the height of the web is 1200, thickness of the web is 12. That gives us 100 of a ratio, and that's greater than 72 epsilon divided by nu, where we have epsilon that we've already calculated from table 5.2 is 0.92 in there. So that tells us that shear buckling resistance for webs without intermediate stiffness should be according to section 5 of EN 1993, part 1, part 5. And we go to that clause 5.1 in Eurocode 3, part 1, part 5. 10 webs are classified by 5.1 part 2 in this code in 1993, part 1, part 5. And it says that the plate girders that have a height of the web divided by thickness of the web, if it's greater than 72 epsilon over nu for an unstiffened web, or if we have a stiffened web, it's this ratio here, then they should be checked for shear buckling and provided with transfer stiffness at the supports. Okay, so we need to do that if we exceed those limits. And then for the unstiffened or stiffened webs, the design resistance for the shear should be taken as the design resistance for the of the web buckling and the flange buckling, shear flange buckling, shear web buckling. So add them two together, and they have to be less than or equal to the overall shear resistance of the section, which is given by this equation here. Okay. So what we usually do in our design is we first say, well, we'll only use basic, not basis, basic. That's supposed to be basic. Basic tension field action. In other words, that we're just using relying on the web buckling, and we'll ignore the flanges. So that's the first thing we'll check. And if that's not good enough, if we haven't enough capacity within our web buckling, then we go and bring in our flange buckling in there as well. So that's what we did last time. We checked for the contribution of the basic tension field action, which is the contribution of the web. So it's the web buckling resistance, which was equation 5.2 in Eurocode 3, part 1, part 5, where we have this reduction factor times the shear strength, so this is the shear strength, these two over each other, times the shear area, which are these two together, divided by the material factor of safety. Okay, and similar to what we've done previously in other examples where we're trying to get a buckling capacity, to get this the shear buckling factor, we need to work out what the normalized slenderness value is first. And the normalized slenderness value is given from table 5.1 and figure 5.2 within Eurocode 3, part 1, part 1, or 1 part 5, which is 0.76 into the square root of the yield strength of the material divided by the elastic critical shear buckling capacity of the section. The elastic critical shear buckling capacity of the section is the shear buckling coefficient times the web buckling stress in there. We'll go to Annex A to work out these two guys, which then we can work out the tau CR, which we put in here. We know this is 275 newtons per millimeter squared, and that gives us a normalized slenderness value. Okay, so that's what we go to. So we go to Annex A and then equation A1. We can see here that the elastic critical plate stress here is sigma E, which is basically 190,000 times TW divided by HW squared. So we put that in, TW HW 12 divided by 1200 squared, and that will give us 19 newtons per millimeter squared. So that's the web buckling stress. So that's tau E. So then we have to work out what the K tau is. So last time we had the spacing of the stiffness has been 1250. This time they're at panel 1 in the middle, panel 4 in the middle, it's 1600. The other panels are 1400 apart. So we need to work out what the tau is for those. So that's what we're going to do. We're going to do now. Okay, so this is equation A5. So in the panel 1, which is the in panel, So in that panel, we have the A is equal to 1400 millimeters. So that's the distance from the stiffeners. That's the distance between the stiffeners. So we have that implies that the area divided by the height of the web is equal to 1400 divided by 1200 in there, which is 1.17, which is greater than or equal to 1. That implies that k tau is equal to, so we're using that first equation because it's greater than or equal to 1 plus 4 into the height of the web times the spacing of the stiffeners squared plus k tau SL, and that's equation A5 in Eurocode 3 part 1 part 5. That's why I have the superscript 5 in it to show that it's Eurocode 3 part 1 part 5. Okay, so we know that last bit is 0 because we've got no longitudinal stiffener in there. We've only got transverse stiffeners, so 5.34 plus 4 into 1200 divided by 1400. So we're checking panel 1 first because that's the one that has the highest shear. We know from the shear force diagram, the ones at the edge of the highest shear. So 8.28. Okay, and we know, so we had that we had tau of E that we've already worked out, or sorry, sigma E was 190,000 into the thickness of the web divided by the height of the web squared, which is 190,000 times 12 over 1200 squared, which is 19 newtons per millimeter squared. So that implies that the critical shear strength is equal to k tau times sigma E, which is 8.28 times 19, which is 157.3 newtons per millimeter squared. Okay, so that's the critical shear buckling stress. So then we can get that, put that in to get the normalized cylinders value out. Okay, so normalized cylinders value, we said it's 0.76 into the square root of Fy of the web divided by this elastic critical buckling capacity, which is 0.76 in the square root of 275 over the value that we just worked out, which is 157.3. So that normalized cylinders value is going to come out to be equal to 1, I think. Got that right. So then from figure 5.2 in Eurocode 3 part 1 part 5, we go to the value of 1. We come up and hit the curve. In this case, it doesn't matter whether it's a rigid impost or a non-rigid impost because they're both on the same line here. So we don't have to worry about which one we have in terms of our detailing. Okay, so we come across there. And from that we get 0.83. Okay, so the reduction factor is 0.83 from equation 5.2. Okay, so then we have the shear buckling resistance is equal to that reduction factor times Fy, the web, times the height of the web, times the thickness of the web, all divided by square root of 3 times gamma M1. So that 0.83 we just worked out, 235 for the for the yield strength. Height of the web 1200, thickness of the web 12, divided by the square root of 3 times 1 for the partial factor of safety. Put all that in, we get 180, 1898 by 10 to the power 3 newtons. So we get the shear buckling resistance of the web is equal to 1898 kilonewtons. Okay. And we know that the shear demand VED for a shear force diagram, what was that? It was 2,100 kilonewtons, which is greater than the web buckling resistance. So that means that the web buckling isn't good enough on its own. So that means that we need to get some contribution from the flange as well. So shear resistance contribution from the flange required. Okay, so this is the one of the main differences between the first example and the second example. In this example, we're pushing the section harder, and that the web alone isn't good enough to withstand the shear demand, so we have to take into account the contribution of the flange in there. Okay, so what is the flange contribution? Okay, so that's the flange contribution that we're going to do. So the flange contribution, if we look in the code, it'll tell us that so this is not going to be full tangent field action in there, so we're going to have the contribution from the web, which we just checked out, plus the contribution to the flange to give us the overall shear buckling resistance of the section. Contribution from the flange in there when the moment demand is less than the capacity. You have the width of the flange, thickness of the flange. FYF is the shear strength of the flange. C is a factor down here, which is A is the distance between the stiffeners. BF thickness of the flange, or the width of the flange. TF thickness of the flange. FYF is the yield strength of the flange. FYW yield strength of the web. HW squared, so the height of the web squared, and T is the thickness of the web. Okay, so that's that factor that we can work out. Gamma M1 is the partial factor of safety, which is equal to 1, and then we have the demand divided by the capacity of the section. Okay, so we need to work all that out. But let's go back to have a look at where we are. So we're looking at the flange contribution. So just remember that we're looking at the different sections or different parts of the beam. So the very first part of the beam that we're looking at is this part of the beam here, where we've got the first stiffener as a distance of 1400 millimeters in. We have the load on the top. N is equal to 420 kilonewtons per meter. We also have the reaction here at A, which was 2,100 kilonewtons. Okay, and because we cut the beam then off here, so we're going to have some sort of moment that we have to design for as well in that panel. Yeah, so we have a panel that we're going to have to design for a shear, which is VED. VED, which is the reaction at A. We have a load, 420 kilonewtons per meter, and we've got a moment at the other end, 1400 out. And this is your first panel, so this is panel 1. So this is panel 1 that we're designing for. Okay. So what is that MED? So MED, so the moment on panel 1. is going to be equal to force times distance. So what's the force times the distance? So we have this is a force going up the way. Its distance away is 1400 millimeters or 1.4 meters. So it's going to be force times distance. So that's the first one. Force is 2,100 kilonewtons, and the distance is 1.4 meters. So that's the first one. That's going up the way. That's going clockwise to balance out the way I've drawn MED1, which is counterclockwise. And then what else is going the other way? Sorry, so counterclockwise, we've got the load coming down the way, which is 420 kilonewtons per meter length. We have it's acting over a length of 1.4 meters, and then the centroid of where it's acting is 1.4 meters away, divided by 2. Okay, so it's this 420. It's acting over this 1.4 meters here, and then the center of where it's acting is equal to 1.4 meters out divided by 2. So that's 1.4 divided by 2. So I work all that out, and I get 2528 kilonewton meters. If we remember from the previous step, we worked out what the moment resistance of the flange was, which is the same across the whole of the length of the member, which is 5,074 kilonewton meters. It's from the previous calculations. Step 2. Yeah. So we can see that MED1 is less than MFRDs. So that implies that the shear buckling up, the shear buckling resistance on the flange V B F or D is equal to the width of the flange times the thickness of the flange squared times the yield strength of the flange divided by C all over gamma M1 into 1 minus the demand, that part of the section that we're designing, divided by the capacity squared. And that's all from equation 5.8, Eurocode 3, part 1, part 5. And that's where C. So that's C is equal to A into 0.25 plus 1.6 times BF TF squared FYF all over the thickness of the web times the height of the web squared times the yield strength of the web. Okay, so we're going to work those out, and then we get the capacity of the flange. So let's work those out. So we'll do C first. So the spacing to the first stiffener, that's 1400, so that's A, into, what do we say, 0.25 plus 1.6 times the width of the flange, which is 500, times the thickness of the flange squared, which is 30 squared, times the yield strength of the flange is 275 newtons per millimeter squared, all divided by the thickness of the web, which is 12, height of the web, which is 1200 squared, all by 275 newtons per millimeter squared. So when we work that out, that should give us 408 millimeters. Okay, so that's the value of C. So then we can substitute that in for the buckling shear resistance of the flange, shear buckling resistance of the flange, which is BF, so that's 500, times TF squared, this is 30 mil squared, take as the flange squared, times the yield strength of the flange, 275 newtons per millimeter squared, all divided by C, which is 408, times the gamma M1, which is just equal to 1. All that into 1 minus the ratio of the moment demand in that section. We're designing for 2528 kilonewton meters, divided by the capacity of the flange for buckling, or for bending capacity of the flange, was 5074 kilonewton meters squared. That'll give me 228 by 10 to the power of 3 newtons, which is 228 kilonewtons. Okay, so that's for the first panel that we've just designed, or we're just checking, that's 228 kilonewtons for panel 1. Okay, so it's just specific to panel 1. Why is it specific to panel 1? Because specific to panel 1 because we put in the demand, the moment demand for panel 1. So for panel 2, the moment demand will be higher, but the shear demand will be lower. Okay, so we need to check every individual panel. So then the overall buckling resistance of the shear buckling resistance of the section is the shear buckling resistance of the web plus the shear buckling resistance of the flange. And we got the web component was 1898 kilonewtons plus 228 kilonewtons. Add those together is 2126 kilonewtons. Okay, so this is the shear buckling resistance of the section at panel 1. Okay, and that 2126 is greater than or equal to VED for panel 1. Yeah, that's for panel 1. So therefore it's okay. Okay, so that's the shear resistance of it. So we know that the panel 1 is fine in terms of shear. We've just checked it. We said that we needed some of the flange to withstand the shear, but only a little bit in there, and that we used all the web to withstand the shear, and that we're still okay. Okay, so let's just look at each of these individual panels then to see what the forces are in each of the different panels of the demand. Okay, so we only have to do half the section. So we have up 1, okay, so panel 1, panel 2, panel 3, and panel 4 goes over the other side, so it keeps going off then, but it's symmetrical, so we don't have to worry about the other side. Okay, so this is VED. So it's 2,100 kilonewtons there to start, and then because it's symmetrical triangles, we've done this previously. It's 512 in there, 924 here, and here for panel 4. That's panel 4 in there. That's 336 kilonewtons. Okay, so that's the shear force diagram, all in kilonewtons. And then the bending moment diagram, again, we've shown how to calculate this, and I've calculated the first version of this already. So we'd already worked out what the MED at the bottom was at panel 4, which is 5250. I think getting all these other panels matching up. Okay, so panel 1, 2, again 3, and 4. We've just worked out that one as 2528. kilonewton meters. And then we can do the same as we've done for that one for all the rest of them. When we get 4,223 kilonewton meters, and then 5,115 kilonewton meters. So you need to learn how to do these if you haven't already learned how to do them. I've just demonstrated for the first one here, and then this one's the exact same way to check it, and the other one's the same way to check it, or the area under the curve up above. Okay, so that's the moment. Sorry, the moment diagram in kilonewton meters. Okay, so we have panel 1. We just checked. Well, we had VED is equal to 2,100 kilonewtons. MED was equal to 2,528 kilonewton meters. Panel 2. VED, in this case, is 1,512 kilonewtons, and the moment's getting bigger. Obviously, it's getting closer to the center. 4,223 kilonewton meters. Panel 3. VED is 924 kilonewtons. MED is 5,115 kilonewton meters, and panel 4, VED equals 336 kilonewtons, and MED is equal to 5,250 kilonewton meters. Okay, so there's all the different panels in there. So what can we notice from those? Well, we've already looked at panel 1. If we look at panel 2 in there, we can see that this VED is less than or equal to the shear buckling capacity of the web, which we worked out as 1898. So therefore, we don't even need any of the flange in there. And that's the same, obviously, for this one here, for panel 3 and panel 4. And we checked the top one there, which is greater than VBRD, which is equal to VBWRD plus VBFRD. Okay, so that's all the panels. So what does that kind of tell us? Well, it tells us that there's no need to calculate the shear buckling capacity of the flange, the contribution to the flange for panel 2, 3, or 4. So do not need to calculate. So we don't need to calculate the shear buckling capacity of the flange for panels 2, 3, or 4. As web shear buckling capacity is adequate. Okay, so it's kind of handy for us means that we don't have to do all that check, so we don't have to go back. And so if we look at here, it saves us having to do this check or this calculation for panel 2, 3, and 4, because we have to get the moment at each of the panels divided by the capacity of the bending capacity of the flange alone, by the moment demand in there to work out what the capacity is for shear buckling of the flange. We don't need to do that for panels 2, 3, or 4 because we can see straight away that the shear demand for each of those panels 2, 3, and 4 is less than the capacity of the web alone. So we don't even need the flange in there. So that's handy to know in there. So let's look at the moment of shear interaction check now. So just a recap, so the moment of shear interaction check is given from clause 7.1 of Eurocode 3, part 1, part 5 in there. And that's basically telling us that if there's no need to check for moment and panel shear, moment and shear interaction if the demand, in terms of the shear demand, is less than half the capacity of the shear capacity of the web alone, then that means it's low shear, or if the moment demand in the panel is less than or equal to the capacity of the flange alone, then we're fine, we don't have to check for moment and shear interaction. Otherwise we do. So let's have a look at that. Let's start doing calculations. Okay, so let's just remember what the numbers are right up the top of the page here. So the moment resistance of the flange is equal to 5,074 kilonewton meters, and you know that if the moment demand of a given panel is less than or equal to the flange resistance, implies no need to check moment and shear interaction. So moment and shear interaction check. Okay, and then R. So we know that the half the web shear half the web shear resistance is equal to, so the web shear resistance is 1898 divided by 2, which is 949 kilonewtons. We know that if the shear demand of a panel is less than or equal to half of this web shear buckling resistance, then there's no need to check moment and shear interaction check. Okay, so because in the first one that means that the moment can be carried by the flange alone, and the second one it means it's low shear. Okay, so that's why. So let's have a look at different panels. So we usually do this by a table. Seems to be the easiest way to do it. So you panel 1, 2, 3, panel 4. Okay, so we have moment, we have the shear. So from our shear force diagrams and our bending moment diagrams, which are back here, from the shear force diagram to bending moment diagrams, we've worked out what the shear force and the bending moment demand is on each of the different panels. So in panel 1, we said that the demand in panel 1 was equal to 2528 kilonewton meters. The moment demand for panel 2 was equal to 4228 kilonewton meters. The moment demand for panel 3 was equal to 5,115 kilonewton meters, and the moment demand for the panel in the middle was equal to 5250 kilonewton meters. Okay, so then so we check those to see if they're less than or equal to MFRD, which is 50,074, less than or equal to 50,074 kilonewton meters, and that one is. Okay, so less than or equal to 5074, that one is. So they're exempt. So it's exempt from checking moment and shear interaction because those two come in. The next one is not equal to, it's not, so that's greater than 5074 kilonewton meters, so it's not exempt, and that's greater than 5074 kilonewton meters. So we can see that panel 1 and panel 2 are exempt from checking for moment and shear interaction due to the fact that the flanges alone can carry the moment, whereas panel 3 and panel 4, that the demand is higher than the capacity of the flanges alone, so therefore they're not exempt from the moment. But let's check for shear. So we have the demand VED1, VED2, VED3, and VED4. Okay, so we had 2,100 kilonewtons, we had 1,512 kilonewtons, and 924 kilonewtons. So again, this is all from the shear force diagram. 336 kilonewtons. Okay, so we can see that the first one is greater than 949 kilonewtons, so it's not exempt. That's greater than 949, so 949 being half of the shear buckling resistance of the web. The next one is less than 949 kilonewtons, so therefore it's exempt. And the last one is less than 949 kilonewtons, so that's exempt. So in this case, what we can see is that panel 1 and panel 2 are exempt as a result of the moment, whereas panel 3 and panel 4 are exempt because of the shear. So they have low shear demand in there. So therefore, all of the panels are exempt either due to shear or due to moment. So panels 1 to 4 are exempt on either low shear or sufficient moment capacity in the flanges alone. Okay, so it's kind of handy. We can see that panel 3 is pretty close in there, so we can see that the demand for panel 3 is 924 kilonewtons, its capacity is 949, so it's very, very close. So we can can kind of note that panel 3 was close. What would happen if it wasn't? So what would happen if that the shear demand was higher than the capacity for panel 3? So let's say, say for instance it's higher. If the VED of panel 3 was equal to 975 kilonewtons, and then if that happens, then thus it's not exempt. Yeah, because it wouldn't be exempt because both the demand, the minimum moment demand, is higher than the capacity of the flange, and it's not deemed to have low shear because the shear demand is higher than, so i.e. VED3 is greater than a half of VBWRD. Okay, so it's greater than half of the shear buckling capacity of the web. So it's not exempt. So would need to check, implies need to do moment and shear interaction check for panel 3. So we're just looking at a hypothetical scenario if panel 3 wasn't exempt. So if we increase the shear demand a little bit, just to see what does that mean. Well, then we have to go to equation 7.1 in Eurocode 3 part 5. So what that tells us? It tells us that the ratio, or the utilization ratio, 3, which is equal to nu1 plus 1 minus the moment resistance of the flange times the overall plastic resistance in the section, or sorry, divided by the overall plastic resistance section, into 2 times nu of 3 minus 1 squared. That all has to be less than or equal to 1.0. Okay, so we're getting that from equation 7.1, Eurocode 3 part 1 part 5. Okay, so what are all these? So the first utilization ratio is just the demand divided by the capacity. for this panel that we're looking at. So the panel that we're looking at, so it's 5,115, and the capacity is 5708. So 5708 came from step 2. So that's 0.896. Okay, so we're looking at around 90% utilization for bending moment, demand divided by capacity. So that's the bending moment. What about the shear? This new 3, which is the shear demand divided by the capacity of the web, the shear buckling capacity of the web. So it's we said that we're going to put the demand is 975 and the capacity is 1898. And so it's just above half. So we said if it's less than half, then it's low shear. This is just above half, 0.514, so it's not low shear. So now we can put that into the formula, which is equation 7.1. So it's 0.896 plus 1 minus the ratio of the resistance of flange, which is 5,074, divided by the overall section resistance, 2 times 0.514 minus 1 squared. And that's 0.89, which is less than or equal to 1. So it's less than or equal to 1, so that implies moment and shear interaction check for panel 3 is okay. Okay, so if we had to do it, it's not a big deal to do it, it's just another step. So I increased the shear demand for panel 3 just to highlight how you would have to check it for moment and shear interaction. If you weren't exempt under moment, so in this case, say panel 3 wasn't exempt under moment, and so that we weren't exempt under shear, we increased the demand to 975, just so we could show how we do the moment and shear interaction check. And we use this equation in equation 7.1, Eurocode 3, part 1, part 5, where we have the utilization ratio for bending, we come to 0.896 utilization ratio for shear, where it's the shear demand divided by the capacity of the web alone. That's greater than 0.5, that's why we're not exempt, because it's not low shear. And then we put those values into the equation 7.1, and we come out with 0.89 as the overall utilization ratio in there. Okay, so that's the moment of shear interaction done. Check. And then as per example 1, we then do the transfer resistance to transfer shear forces. So I'm not going to go through that here again, but it's it's the same idea in there. We trial the stiffeners in there. We get the slenderness of the stiffener plate, the buckling resistant stiffener plate, the normalized slenderness value of it. And then we can get this reduction factor again. We get the resistance, the shear resistance, or the transverse force resistance. In this case, it's 1917, and then it's the demand divided by the capacity in there. So we need to make sure that that works, and also the deflection as well. So I think in our case, at the end is 2,100. So in this case, this stiffener doesn't work. We need to increase the size of the stiffener, the cross-section area of their stiffener, for example, in here, to make sure that this is greater than 2,100. Okay, so the previous stiffener wouldn't work for this one. We might need to put a bigger stiffener in there to make it work. And then the deflection check is the same idea as last time, except that we need to have different loads underneath it. But it's just underneath the imposed load that we're going to check. Okay, so that's step 7 is the weld check. So to make sure the weld works in there, this is taken straight out of example 1. But in this case, instead of 1,750, we replace that with 2,100 because that is the shear force. Whatever the same, we have the same area, same cross section shape, so everything else is the same. That gives us what the demand is on the weld, and then the capacity of the weld, if it's a 6 mm continuous fillet weld, is 0.94 kilonewtons per meter run, which comes from the blue book. And we make sure the demand divided by the capacity is less than or equal to 1 in there. So from the first equation, the update that you would need to do is you need to change the demand here from 1750 up to 2100 to work out this new value for the demand, and then the demand updated the value for the demand divided by capacity has to be less than or equal to 1. Okay, that's the steps that we went through. So the big difference in this one was basically that we had to utilize the flanges for the contribution of the flanges for the buckling resistance of the section. Another difference could be in our design that we might need to take into account is that we might end up with a class 4 web. Okay, so when the plate girder web has a class 4 section, so in that last example, the first two examples I've done, the web section was a class 3 section, but we might end up with a plate girder that has a web of a class 4 section. In other words, it's a cylinder section, and we could have a class 1, 2, or 3 flange. So then, how would you calculate the moment capacity of the section? Well, the conservative approach would consider only the moment resistance of the flanges to the calculation of MFRD. So in other words, I could say, look, it's a very slender web in there, so I'm just going to ignore the web in terms of the moment resistance, and if the flanges alone have a capacity of higher than the demand, then that's it, that's done. I don't need to worry about trying to work out what the moment resistance of the web is because it's relatively small compared to that of the flanges. So I could just follow step approach 1 here, or in approach 2 I could go for a more exact approach through calculating of the effective elastic modulus of the section using the reduction factor in accordance with section 4.4 of Eurocode 3 part 1 part 5 and table 4.1 of Eurocode 3 part 1 part 5. So obviously the easiest one to do is do option 1, which is to make sure that the flanges have good enough resistance to be able to withstand the applied moment and not worry about the contribution for the web in terms of buckling or in terms of bending resistance. Or if you want to go for a more exact solution, then you can work out what the effective elastic modulus is of the section. Okay, so note a class 4 slender web relates to local buckling and is not to be confused with a thin web. So a thin web is when we look at the height of the web divided by the thickness of the web, and that we check it for shear buckling. So this is local buckling where we're classifying the web as class 4 according to table 5.2 in Eurocode 3 part 1. Okay, so that's one thing to watch out for. Next tip as well to keep an eye out for is obviously you're trying to size up your plate girder for your project. So where do we start? So in 2 examples I've done, I've given you a section or a plate girder size to start with and then worked out to see if that plate girder was adequate or not to carry the loads or demand on it. But we may need to, usually as a design, we don't know what size is going to start off with, so we have to make some sort of guesstimation of initial size of a plate girder. And this is my tips, I suppose, for getting the initial size. First thing is, well, we want to decide on what the depth is of the plate girder. So if we take the depth as being the span, so the length of the beam, divided by a ratio somewhere between 8 and 15. Obviously, if you take 8, you're going to get a bigger depth. If you take 15, you're going to get a smaller depth. So 8 means you're going to get a bigger depth, so it's going to be more conservative. 15 is a smaller depth, so it's going to make the beam work even harder, the members work even harder. So somewhere in that range in there. Obviously, the architect or the client prefers you to keep the depth of the beam as small as possible because therefore you get more head height into the room or the overall building is lower in there. But you have to balance that out. Usually if you have a shallower beam, it means you have you may end up having a heavier beam, more steel in it, because you can't keep the flanges far enough apart to improve their moment resistance. Okay, so that's the first thing. So pick a depth somewhere between, by taking the span, divided by somewhere between 8 and 15 in there will give you a first trial depth of it. Then we need to decide on what the flange areas are. So what plates we're going to use for the flange on top and the bottom. And the recommendation there is basically take the moment demand from your bending moment diagram, and you want to match that up with your resistance from the web or from the flanges only, which is the area of the flanges, the height of the flanges, so how far they are away. So we pick the overall depth of the section. We're going to put them far enough away from each other, and Fy is the yield strength of the material. So basically so we want to make sure that the demand is greater than or equal to the capacity. Sorry, the capacity is greater than or equal to the demand. We know what the demand is from the bending moment diagram. Okay, so we know that the capacity of the section is the area of the flange times the height of the flange times the interior property of the flange has to be greater than or equal to MED. So what are we trying to work out? Well, we're trying to work out the area of the flange has to be greater than or equal to MED divided by the height of the flange. Well, sorry, the height of the centroid. Okay, so if you remember the section, that's the height. Oh, come back, sorry. Okay, so that's the centroid of the top flange, centroid of the top and bottom flange. So in step one, we've set the overall height of the section. Okay, depth h is equal to span divided by 8 to L divided by 15. So somewhere in that range, we're going to set the overall height. So we pick a height that's within that range. So that's step one. Then step two, we're going to decide on the flange area. So the flange area is going to be whatever the moment demand is from our bending moment diagram. So we've got a bending moment diagram in there. We've got the maximum moment. We have the height of the flange, or sorry, the height of the centroids of the flange, Fy, which is the yield strength of the flange. So if it's S275, it could be S275. So we'll have to assume what the thickness is here in this instance before we can work out the area. So if I make the thickness, say 30 millimeters or 40 millimeters or 20 millimeters, so I just pick a thickness. Once I know what thickness, I can then come in that half the thickness from the top, half the thickness from the bottom. That'll give me HF of the overall height in there. And then I can work out what the width is of the section. So I assume a thickness. So in step two, we need to assume a thickness, and then by assuming the thickness, then we can work out what the width is here, because AF is obviously so AF here is the width of the section times the thickness. Sorry, the width of the flange BF times the thickness of the flange TF. Okay, so that's step two. So now we've decided on the overall height of the section. We've decided on the top flange and the bottom flange from step two. And then what about the web? To get initial web thickness, TW, use class 3 boundary conditions. So class 3 boundary conditions is saying that if it's a class 3 web, the height of the web divided by the thickness of the web has to be less than or equal to 11.4. So therefore, I know what the height of the web is because I've already set the overall height of the section. I've already set the thickness of the flanges. So the height of the web is obviously going to be equal to, so the height of the web is obviously the overall height minus twice the thickness of the flanges. So I've set that. So therefore, I can work out, the thickness of the web has to be greater than or equal to the height of the web divided by 11.4. Okay, so that's step three. So now I've got the thickness of the web up here. Okay. So I've got all the main properties of the section in terms of the flanges, the web, bottom flange in there by doing those three steps, and that's initial start. So at least I'm not just stabbing in the dark of what size it is. Obviously, this first step is a big range, 8 to 15. So it depends on where I pick within that is going to make a big difference in terms of the size of the other things. So your project, we need to try and keep that main beam less than 2.8 meters, and the other beam, if you need to do a plate girder section, you might be able to do a roll section, depends on your loads, but keep that one less than 1.2 meters. So that's the aim, so no higher than 2.8 meters in your own project. And remember to use plate girder self-weight in the design, because that can be pretty heavy because all these materials here, so make sure you include that in your design in terms of loading onto your beam. Okay, so that's the tips for your initial design. So 3 steps there to get the sizes of different plates. We're aiming in this example that you're doing as part of your project to keep the overall height of the beam less than 2.8, or for the shorter span ones less than 1.2. And as always, when we're designing plate girders, we need to make sure for sure to keep the self-weight into account when we're doing our design, because it can be pretty substantial. Okay, so that's the examples done for the plate girder and the theory going with it.